So that is also part of it. I felt like
The lifestyle. It's a lifestyle. It's a jungle lifestyle.
exactly.
I'm not married to the method.
I have to start.
How do you know all of this, but you're not a member? Hey, Adam, you're making me a little skeptical. You might be a secret shrine. You knew about the magnets. You knew about everything before I even said it. What you do with the journey? What you do with the journey? Make first you notice it. You get mad. You're secretly mad.
I always follow
That's an ICP show. Oh my god.
I'm just testing my pins. They work. This one's the dead one.
Is this going to be an example?
Cats.
Yeah, we started, I'm a minute late, so class business first, because we're winding down and a lot of little things gotta get done. Finish up, start simple. Last homework, these are, I know the one guy never writes the total scores at 73. Your average is shot up 95% on this, so very good. Unless you didn't turn it in, which is a big screw up. So I'm sure this last one's going to come out fine. And again, you'll have till, I'll wait till 5 o'clock when I have a meeting. Definitely all post answers. One of you pointed out I screwed up the link on video, on Monday's video, so sorry about that. If you ever noticed something didn't work, generally you actually just name it. So I had linked lecture 32, it was actually lecture, sorry, 40, it was actually lecture 42, so that's why that got screwed up. So if you ever, in the last 4 or 5 lectures, if you're having trouble, you might want to just look at the link that may have just misnamed it. I will try to make that mistake, but anyway, it's up now. And let's see, Friday is supposed to be a double lecture because of, remember test 3 is the following Friday, and the following Friday is the last review. I'm not going to do that because with the material I will cover by the end of the day, this next Friday, 2 days from now. Again, that is all the material that is ever traditionally taught in PChem 1. I've done it. That doesn't mean I'm going to stop. And what we'll do is on the second lecture, we'll continue, even with the test coming out, we'll continue the policy of going over some 346 stuff to get you ready for that. And I'm going to do differential equations. So, as I showed a little bit, quantum mechanics is a differential equation thing, meaning that you're doing integrals. That class is harder. Also, kinetics. Kinetics is done in 346, and that again is solving differential equations. So we'll do that on Friday. Meaning we won't review Wednesday, just kidding. We'll review on Wednesday as normal. I don't know that I can go the whole hour. This has been a relatively easy last section. But with that said, let me warn you. Guess which one is traditionally the lowest scoring test?
3.
3, because lots of reasons. For one, I think it is so easy. I mean, your scores just shot up, so you might be taking it too easy. Right, yeah, you still need to read through your notes no matter what. You still need to do that. If you don't, it will hurt your grade, even though this stuff is easier. So I think people just really get slack. I mean, plus it's the end of the semester and everyone's tired. Between that and thinking that it's going to be so easy, people have, every time I've taught this, test 3 is the worst. And it should be the highest. So don't look at that. It just kind of sucks for us both. It makes it harder to grade too. I don't like that. So again, we will review on Wednesday, and if anything, I'll just drop a bunch of hits on what's on the test. How about I just do that? Because I don't have anything else to talk about. In terms of other test material, like what you just did, I just start reviewing freezing point depression, boiling point elevation, solubility. The solubility equation is there's so many approximations, it's next to useless. That's why I didn't even ask you about it on this homework. What I don't have on the test is I'll come up with another relevant example. It's hard to find a better example than salt water because that's pretty relevant, but I'll find something. And I'll just ask you to compute some numbers and compare it to a real result, and it'll have that much meaning, but it'll be a calculated question. And so then the Friday after that, we have the test 3, and no homework, by the way. I'm not going to post an 11th homework. If I do anything, that's because, I'm sorry about this, I don't mean to sound slack, it's just that gives me 1 week to grade a problem set and 2 tests, one of them being your final. I can't do that. If I did nothing else but grade, I could. But unfortunately, I have other stuff that they make me do. I've got my grad students, I got meetings, I just can't do it. So, depending on the difficulty of the material, if I think you need some help with some example questions, I'll post a fake problem set 11 that you don't actually have to do. And I'll even wait to give the answers, but I don't think we're gonna do that. Because like the material today, there's no equations in the material. Sorry, there's 1 or 2 equations, but they end up being graphed, and that's what I'm gonna test you on. I'm not gonna test you on the equations that we're gonna derive today. I'm saying it's easy. It's ridiculously easy. You don't need problem set questions to get the test set questions right. I mean, the difference between this and DH, DV at constant T, I mean, that stuff is just completely different league. So, maybe I will, maybe I won't. I don't promise anything, but don't worry about it. I'm not trying to be slack, it's just I just don't think you need any help. What we're going to cover instead, I got 3 lectures to come up with. Because 444 is now being removed, which normally you were required to take that, not you engineers, you chemists. You used to have to take that just a few years ago. And because of credit hours, it had to be taken off the table. I'll do 3 lectures of 444. And this is good for you, right? This is kind of semi-graduate level, and that makes you better than the Northwestern and the UC, whose only advantage is money. Their family's money. Unfortunately, that's a pretty damn good advantage. All right? So I have to pump you up that much more. What we're going to cover is a non-mathematical science of topology, molecular topology, called group theory, which is mostly what 444 was, which is really easy, by the way. And I reserve the right to put that on the test. And if I come up with some questions on the test that are kind of hard, then definitely you'll see that 11th problem set. So I'll make sure that, you know, if I come up with some problem, what kind of problems could I ask? Let me work on the lectures, think of questions I might ask, write them, and then tell you about them before the test, which I will do in time. Oh my God, I'm running my mouth. What did you talk about? Any questions? You guys, you're okay? No one? All right, well, okay, let's completely change directions. I don't even want to write anything about the equation, but this is the equation for freezing point compression. This is the equation for whatever. I'm not going to rewrite it because that's kind of pointless. It was all very simple derivations with Gibbs Helmholtz. Gibbs Helmholtz comes up a lot, sure. But I'll just, watch the last video. I won't go here with you. So today we're going into multi-component phase diagrams. That's why the engineers, I think, are virtually missing because they've already had this stuff. And let me just, all right, so what we're going to start out today is I'm going to show you like the liquid or vapor phase diagram of like ethanol water. And let's get into why that is actually slightly difficult. You can give phase rule, C minus P plus 2 being temperature and pressure, we know that. Okay, now normally, if C was 1, I've got 1, and let's say that there's 1 phase present. Okay, that's 2. That's T and P, essentially. That's easy to draw on a board because it's 2-dimensional. And I can draw 2-dimensional objects on a board. Okay, now let's make C, and then of course, if I have 2 phases, those are the lines, then I have 1 degree of freedom. That I can definitely draw on a board. And if I'm at a triple point, then I have no degrees of freedom, which is a point. And I'm certainly capable of making a point on a board. Okay, let's do C equals 2, E equals 1. Again, this is the hard, sorry. Equals 2, E is equal to 1. This is the plane. I've got 2 minus 1 plus 2 is equal to 3. Now that's a problem. Again, some of the issues with this are, up until major computers existed, I have to be able to draw this, and you have to be able to draw it back, and we have to use this stuff. And we have no choice but to work with flat things. It's becoming less true, especially if your tablets end up being 3D, which is what God knows Apple is working on. I'm sure it'll be cheap. And so let me point out, yeah, right. Let me point out how this looks. Okay, and TP is easy, but now, basically, I've got a third dimension which is mole fraction. So now I have to draw this beta in the form of a cube. So this is an object inside a cube that shows solid regions, some weird shape that if I'm in that position, I'm a liquid, and if I'm in some other different colored solid part that fits right into the liquid part, that would be the vapor region. I can't do that. Now again, with some kind of crazy computer rendering, I can imagine it'd be like rotating so you kind of get it, or an actual three-dimensional, where the glass is, it would be viewable, but I have a two-dimensional board, I have to make compromises, I have to make approximations. The question? Oh yeah, PT, whatever. It doesn't matter. You're right. The way I've done this before is PNT. Either way, it's a cube. The important thing is it's a cube, it's not a piece of paper. So, everything I'm going to do today is to take this and render it in a way that makes sense, and there'll be some parts of this where it's like, okay, this is how pressure works, and this is how condensation works. The first thing we're going to do is hold temperature constant, so let's make T 298. So that way I'm going to return to a two-dimensional representation of mole fraction versus pressure. So big picture. So the hard part about this, now again, I stated all of this is incredibly simple, but it's a little hard to follow. So focus, right? You got to really focus. If you and you get distracted, if you miss something I say, you could lose all of it. So now we've got videos. So again, get rid of T, hold T, don't get rid of it, hold it at 298, and then do P versus mole fraction. And again, this is a phase diagram. I need to have phases. And I'll do liquid and vapor phase first. And fortunately, it actually gets kind of complicated. This is much more complicated than the single component phase diagram. Like number one on your homework, it's a lot more complicated. And it requires some derivation to do this right. And the first one, let's do total pressure of something as a function of mole fraction in the liquid phase. Okay, now, again, I have to go real slow with this so that you know exactly what the heck is this, because the answer, by the way, is, why is this complicated, is because I'm going to put one phase diagram and then I'm going to draw another phase diagram on top of it. That's why this is a little complicated. Not complicated, it's hard to follow. They're different. Okay, now I'm going to have mole fractions in the liquid phase. I'm going to go from 0 to 1. And I'm going to have partial pressures of the vapors in the vapor phase. And of course, if it's boiling, it will be 1 atmosphere, because that was the part of 5 and 6, right? To know that thing, and I said this in class, things boil when their partial pressures are 1 atmosphere, or whatever you're, we're slightly less than, we're at 1 bar, right? Okay, so again, this will be the total pressure, and actually, already, I'm going to make this interpretation. And this doesn't matter, by the way, just so you know what I'm trying to do. Let's define P total as the partial pressure of A and the partial pressure of B. Okay, now there's a partial pressure of C, which is air itself. Let's just wipe it out, all right? It's just too hard to throw that in, and it just doesn't do anything. So I will define the total pressure as just of those parts of the tube liquid. And I know that they have partial pressure, because like later tonight, when I pour some water and ethanol together for no reason, I can smell it, right? I know I can smell the water and that extra magic juice, and I know that they're there. And that's because they have a certain total partial pressure, which is around 600 pascals, right? 600 pascals in a pressure of roughly 100,000 pascals, right? Again, because we're slightly above sea level. All right, now again, we're going to make approximations. If I define it this way, then I know that if I have all of water, then the partial pressure will be that of water. And then I'm adding ethanol, and ethanol, I believe, does actually have a higher partial pressure, and so this will be all of PA. It kind of makes perfect sense. Now, we've already done this. Sorry, I should have a little tape up there. Straight to the tape more from the side, that doesn't really work. There we go. Okay. Now, we did this with Henry's law and Rayout's law. Actually, I'm using Rayout's law, if you recall. I'm supposed to do this after Rayout's law. It's just I hope that we would never actually get to this, because it's freaking boring. So, here's a neat thing about p-tote. Okay, so I've got, we're going to use Rayout's law. So, fine if something's pure. If we're in the middle, this is clearly wrong, but just to make life not impossibly difficult, we're going to just stick with Rayout's law. So all this is ideal. Okay, and what I'm doing, by the way, I'm deriving this line, an actual functional line. Last time I just drew it. And the first thing to do is recognize that I've drawn an axis. I only have one x-axis, that's chi A. So I need to get rid of chi B, which is very easy. I can't draw little stars. I don't know that. I never can get that right.
Minus chi A. 1 minus chi A.
Chi A, right. And right hand out if I screwed up, right? Thank you. These number of handouts I've ever written for a class. Okay, so then chi A, I'm just distributing, because this is childish. Plus PV, star, minus chi A to B, star, minus root of star. And now what I'm going to do is just rearrange and factor PV star plus chi A. Let's say I have PA minus PB. Okay, again, this defines the line that I just drew. Now, I can imagine, I can almost do this phenomenologically. I did use Rayout's law. This is an obvious fact of numbers. And then I just did some algebra. I mean, look at this. It really is sensible. If there's no A present, then that's 0. And so I have the pure partial pressure of B, which I did. Very simple. If this is 1, the PBs get subtracted, leaving me the pure partial pressure of A. It's just childishly simple. So there you go. Now, again, remember that this is the partial, this is the pressure of the vapor phase. As a function of the mole fraction of the liquid, and again, it's an ideal solution. But we all know that the vapor phase could be different. So what I need to do is get the total pressure as a function of the mole fraction in the liquid phase, which is not necessarily the same as the mole fraction in the, I need to know the total pressure as a function of mole fraction in the gas phase, which is not necessarily the same as the mole fraction in the liquid phase. So, again, that was part of a lot of problems that sometimes you see those in PSA, but they're really not. Okay, and let me find some new terms. So again, this is why you don't want to get confused. Chi's are going to be for liquids. I'm going to write that down. Chi A and B equal liquids. And of course, we're going to do other phase diagrams than liquid vapor. And then I've got Y. A and B equals a vapor. Or gas phase, same thing. I call it a vapor because again, I'm not thinking about air at this point. I'm only just saying that the atmosphere is composed of A and B, or just forgotten air. Okay, now, this does actually get a little hairy. Okay, that's going to be the partial pressure of A, Dalton's law, over p-total. Okay, the very definition of the partial pressure. Now, if I use Rayout's law, I'm going to say that can be related to the liquid phase. Sorry. Sorry, I'm doing this right. I'm being an idiot. Okay, Rayout's law. I just kicked in Rayout's law. That the partial pressure is the pure partial pressure times its mole fraction, P tote. Right there. There we go. P star plus chi A PA minus PB star. Don't get little stars. Little stars are special. I need to give my cat stars from they're good, which is never. So, yeah. And then let's again look at this guy. If chi A is 0, and I've got chi-A PE over PA star, chi-A is 1, then I've just got, I've got the number 1, right? Yeah, which it should be. Right, okay. So again, it has correct limiting form. It makes sense. I mean, again, I did a little bit of the derivation, but it's very simple. Now, since P, now I've got to get YB, but let me show you that YA plus YB. Right, so this is something different. Is equal to PA over PA plus PD. Remember, because this is the total pressure. So this is the mole fraction of A, and the mole fraction of B is its partial pressure divided by my funny definition of the total for getting oxygen and nitrogen. Mathematically, that's obviously 1, and therefore YB is 1 minus YA. Again, these are mole fractions in the vapor. Oops, sorry. It's ugly. Okay, again, middle school mathematics for you here. Okay, so now I want to start looking at how the mole fraction in the gas phase looks compared to the mole fraction in the mole fraction in the gas phase. It looks as a function of mole fraction in the liquid phase, and we have limited conditions. You see, if PA and PD, let's see different conditions. Let's imagine that the pure partial pressure of A and the pure partial pressure of T are the same, or very, very close. What you have is, let's see, in that case, okay, so that's 0. And I've got chi-A, partial pressure of A over partial pressure of B, but there's no 1, but that's the same. Okay, there you go. And so what does that look like? I'll go over here. Okay, mole fraction in the liquid phase on the bottom, mole fraction in the vapor phase. And now, one thing to be careful here, that this is not total pressure. This is mole fraction in the vapor phase. I'm going to do total pressure in a minute. Now, since this is how much A is present, if there's no A liquid, I ought to be at 0. And it's a line. It's a line with a slope of 1, so I tried to draw it that way. I think I did a perfect job. And when I have all A present, then in the vapor phase is the pure partial pressure of that vapor. Okay, but this is not perfect. Let me show you what else it can do. Okay, let me show you that it makes sense. I'm just going to give one limiting case here. This is what happens if the pure partial pressure of A is greater than the pure partial pressure of B. And the way I know that is that, I mean, this is not the most complicated thing in the world, but I drew it with a graph calculator. Actually, it's MATLAB, whatever. And I'm sure the optical structure of bits count works, but I won't draw that case because I think you get the point. And again, imagine if I asked you to draw that, just use your graph calculator, or you could just even play in a couple of minutes and figure this out. It's very simple. And it kind of makes sense that, now again, I have to start at 0 and end at pure partial pressure because this is the mole fraction of A. But as A becomes more and more present in the liquid phase, and it's more effervescent, I would imagine that I would smell it faster as I started pouring it in than if these, oh, here, I need to draw that. And if partial pressures were equal, pure partial pressures were equal. So again, the word is effervescence. Just like ethanol is more effervescent in a solution, that's why you can smell it really well, or the cops can smell it really well. You can screw up, you don't do that. Is that as soon as I pour the slightest amount in, I can definitely smell it. And that's what this is saying, and the reason is because the pure partial pressure is higher. And again, I hope that just kind of makes physical sense. All right, now this is where, and again, this is the competition, liquid and gas. Okay, now to complicate things. Unfortunately, as I mentioned that I'm going to solve my hypercube, this is technically a by the way, we have to display data, and the data is inherently three-dimensional. I mentioned to you that the solution to this was, again, we have to cut out T. So every time we change temperature, we have to draw a new phase diagram. So we'll just always work at 298.15. The solution was that I draw two phase diagrams on top of each other. And let me start looking at the, on how I'm going to do that. So again, I just noticed very simple radius law manipulations. None of this has been very difficult. But I'm going to start building the second phase diagram, the things that define its lines, and then I'm going to draw those two on top of each other. The straight line one and what I'm about to do. Okay, now the point here is that I have to get the total pressure, not like, so total pressure here as a function of the liquid composition is right here. And again, here's our straight line, our straight radius law line. That is going to be a phase diagram I'm going to draw. Now I'm going to draw another phase diagram which has total pressure on the left, but it's not going to be a function of chi A. It's going to be a function of YA up there. And then I'm going to lay these two on top of each other. So again, big picture, that's what I'm doing. Two phase diagrams drawn on top of each other. Total pressure and composition. Total pressure for the liquid is here. It's done. Total pressure for the vapor. I'm not going to actually do it. It's roughly 20 minutes of algebra, but let me show you how it's done. Okay, so now I've got a sensible equation for total pressure. The problem is it has chi A in it, and I need YA, not chi A. I'm already done with chi A. I've got that phase diagram. I need YA. How do I get it? Well, up here, sorry, put this up here too quickly. How do you actually do this in the trick? Because I just did it, and it does take a really long time. It's just tremendous algebra. I've got my YA and my chi A, and total pressure is a function of chi A. Now, if you look here, it's not hard to bring this over here and to bring this over here. Basically, you can factor your chi A's out. And again, I'm not going to do it. It really is horrendous. You can have chi A factor, chi A equals blah. You plug that chi A in here, and then you get total pressure as a function of not chi, but YA. So that's the strategy. If you're really curious to see how you do it, I've actually, just before class, I actually did it to make certain I know what the hell I'm talking about. It's on my chalkboard by my office, if you're curious to see how it works. Okay, so again, I hope you see how that works. It's starting with our known thing, but I just substituted that out using that thing up there. That's how I did this, but I don't care to repeat it. This is what it comes out to. I'll show you that it has the correct limiting forms, and that's as good as I'm going to do. And if you're really curious, just try it yourself. And yeah, I probably could have just phenomenologically just written an equation that just does the job the right way. Okay. And again, a bunch of linear equations, even if it's one over line. Okay, so again, that's what I get when I do that 20 minutes of algebra. Just make sure it makes sense. Okay, if this is true, if there's no vapor A present, this term's gone. I've got PA, PB over PA. Now remember, if I forget this, if I just write P, I mean total P. Sorry about that. But I've been doing that for a long time. Okay, I just show this is obvious. If Y sub A is 1, again, the only vapor present is that of A for whatever reason. Let's see, I've got PA minus PA plus 1 times PB. So I've got PA, PB over PB, which is PA. Okay, so I contend that this works, even though I didn't do it right. Let's see what it looks like. Limiting cases again. Totes versus YA. Okay, so what this does is, I'll do my, sorry, let me, I draw this as a box. I'm going to do the two limiting cases of, let's see, I'll do, the pure partial pressures are equal, and that'll give me one line. very simple line, and I'll do the case of partial pressure of A is greater than that of B, and then just do one over there for the opposite. Okay, if PB, if the pure partial pressure of B is that of PA, because they're very, very similar liquids, then, let's see, this is 0. That turns to 0. That means that there's no influence. There's no influence of mole fraction. Mole fraction disappears. That means that this has to be a flat line. So then I've got, it looks like it's the pure partial pressure of B in that case. However, the pure partial pressure of B is the same as A, so you can't really say either. So I see I have to have a straight line. There we go. So that one is relatively easy. And of course it's PA, but remember that's the same as PB this time. Now again, get your graphing calculator and make this negative, a small negative term, and it'll look something like this. Of course, it has to still end at the same spot. So there. And then again, this is PA being greater than PB. It looks like by a lot. And of course, this would be PB star. And this would be just PA, so I'll get rid of that so it doesn't confuse you. So now this makes a lot of sense. Again, the pure partial pressure of A is greater then it has to be higher up. That's pretty obvious. And the curvature, again, is due to the nature of this equation, which you just need to use your graphic calculator to see that I draw it right. Okay, now for the hard part, the multi-component phase diagram itself. It's gonna, I'm gonna basically take like this curve and the one I erased, whoops, and I'm gonna draw them on top of each other. And then we're just going to practice how to read it and do a couple of examples. And, okay, again, I'm going to do P total. Okay, and again, remember, I'm actually going to have two x-axes drawn on top of each other. I'm going to have PA higher than PB. It's definitely a bit exaggerated. And if I draw chi A, what kind of line? Curvy line or straight line? Straight, right? Radial slope. Right, remember this is the liquid. And the liquid is just linearly proportional to the total pressure because radial is simple. Okay, and I did this just a little while ago. Unfortunately, I just erased it. Now, here's the crazy thing. I've drawn another one on top of that, which will basically be this guy right here. And it's going to do exactly like I drew it. It's not linear. And again, this is, don't forget that this is the, that I'm just trying to reproduce this curve here. Maybe I'm not drawing it well, but that's the idea. That curve is this curve. It looks similar. Okay, again, two phase diagrams drawn on top of each other. And now we've got to figure out how to read this because I have two x-axes. So, first of all, just like the single component phase diagram, high pressure, low temperature solids, low pressure, high temperature gases are critical. Now I've got to figure out, I've got liquid, I've got vapor, it's really gas, I should call it gas, whatever. And then I've got liquid and vapor. Now I've got to figure out which one's which, because this is probably what I'll do on the test. I'll throw something like this up here. There's many flavors of this, we're going to go through them all. I may pick one and say, tell me, fill out the phase diagram. Okay, now let's look at this. Now temperature is set, but this is high pressure, liquid or gas? Yes. At high pressures, if I pressurize the gas enough, it turns to a liquid. So this is all liquid. Okay, low pressures, if I put water and I decrease the pressure a hell of a lot, it turns to gas. So this is a pure gas. and it makes this the liquid plus gas. Sorry, I should have drawn it a little bit bigger. So in your notes, maybe write out liquid plus gas, so don't get confused about your own notes. Okay, now for how to read this thing. If you're in the pure gas phase, what I'll do is, this is kind of painful. Let me draw a point like right here. So given that this is a 298, because this is the 298 one, again, I have to recreate every different temperature as possible. I have to make a new one. So I'm just going to do the 298 one. I'm just making that up, but whatever. At 298 and at this total pressure, I have all vapor. To know what's the composition of the vapor, I draw a line, and I realize that that is Y sub A. And it looks like it's about 50-50 A to B. So again, because this is the gas phase, the x-axis belongs to Y sub A. And you see why this is easy, but you can lose it if you don't pay attention. Now let's go up here. I'm going to cross the liquid vapor boundary and go right up here. Same deal. This is in the liquid phase region because I increased the pressure. The composition of the liquid, it looks like it's about 50-50 A and B. This is now the chi-A axis because I'm in its region. Now this one, this is where it gets interesting. Right, now these are where the questions on the test 3 and possible final will come from. What do you do with this sucker? Because you've got two phases present. The way you do it is you look left and you look right. And you drop. Drop down just like that. Now, this again, I have 2 points and 2 axes to choose from. So this is, I should have, 1, 2, 3, oh sorry, 0, 1. I should have put that. Now let's forget this line here for now. I don't want you looking at that and get confused. And this is gone because we're not at that composition. Okay, I gave you a point there. You draw left and right, and then drop down. And now you've got 2 compositions, which you should because you've got 2 phases, each with its own composition. But you've got to know which one's which. So on the test, I'll have little tick marks, and this will be 4, 5, and 6. Sorry, 0.4, 0.5, 0.6, right? That's what I'm going to do. I'll make it obvious. Trust me, I'll measure everything. You can do that with the Adobe Illustrator. Now my question to you, 0.4, does it belong to the liquid or the gas? Liquid. How do you know that? Yeah, because it touches the liquid line, and that's the gas, right? So whichever line it touches, this is clearly the liquid line, that makes it chi-A, and that's Y sub A. So there you go. And there's a lot more kind of neat things about this. Let me, I should probably work on this. Just let me draw it a little bit bigger. Lever rule, and I remember seeing lever rule in the freshman chemistry textbook. So hopefully you've seen this before. If not, this is shockingly easy. I can tell you the example I gave above. Again, just like our phase diagram actually hid information like what is the partial pressure of the liquid, which if you just move your line down to where the vapor line was in the liquid region, and that was your partial pressure of the vapor, there's information hidden. Let me just exaggerate this. And I just want to exaggerate the hell out of it, because I should have done it there, but I don't want to erase it either. And I'll draw a line. And I draw a really, really big one here. And I won't even name the phases, because I'll make this as generic as possible. I'll call this alpha. I'll call this phase beta. Because we're going to have a couple more phase diagrams, right? And we're going to even have 3 phase diagrams. We're even going to do those solids at one point. Hello, tomorrow. Okay, here's what's going to go here. There we go. And composition, who cares? At this point, I don't care about composition. I'm going to call this length. I'm going to call it like intensity of the alpha phase, and then I'll call this bit here like intensity of the beta phase. Okay, again, the point is, there's information hidden in this phase diagram more than just composition. And what this is actually the lengths of these lines tell you how the system is biased towards vapor or liquid. And it does it this way. So let's say number of moles of alpha phase times the intensity of the alpha phase is equal to the number of moles of the beta phase times its intensity of the beta phase. Which means that N alpha over N beta, now this is where it gets a little funny, is the intensity of beta over alpha. So it flips. So they're inversely proportional. And, let me do it. Okay, so in this case, they look like they're a little bit equal. So that means that the system, imagine I took ethanol and water and I put it in a box and it's at a certain temperature, maybe it's at a low pressure. Some of the liquid turns to gas. How much gas, how many of the moles have turned to a gas, which is how many moles have decided to retain liquid. In this case, it looks like they're roughly equal. But note that it's basically inversely proportional. Right? It is inversely proportional, so I'm being an idiot. So in this case looks even. If I decrease the intensity of the alpha phase, do I have more alpha or do I have more beta?
More alpha.
Right, more alpha. Right. So again, that inverse relationship. Now, in terms of what I'll ask on a test, and again, this is why I won't even do the reviews on Friday, because it's just too simple. Wherever I took the point, the dominant phase is the one it's closest to. Right? That's the easy way to remember this. So let me go back so you don't get confused with these alphas. So whichever one the point is almost touching, that's the one with the most number of moles. But now there's one thing that's really kind of cool about this, and I may drop it. Let me just stop after this so I can get back to your homeworks. Okay, so here's our composition of the liquid phase. This is one of the cooler things about these things. Now, again, I set it up, and this is where I was at. I just magically decided that. Now, two things about this are kind of cool. Imagine I had not started here, but started here. Tell me, how did the composition of the liquid change? Now, again, I know it looks like I have more liquid, I guess, but how did the composition change? Got bigger, got smaller? Didn't change at all. Now again, I made my mix differently. I started out under different conditions and I'm here. What's my composition of the liquid?
Same.
Doesn't matter. It doesn't matter how I prepared it within limiting factors. Yeah, okay, I can adjust the pressure. That's right now that's cheating. So I could have poured in different amounts of water and ethanol as long as I'm at the correct temperature for the diagram itself and I didn't change the pressure too much. Of course I can do something really wacky, but within some degrees of freedom, I can change the composition of what I poured in and get the same damn thing. Nothing happens. Does that make sense? That's kind of odd. That doesn't make sense to me. It seems like if it looks like I've added more A, so why don't I end up with more A in the liquid or vapor phase? Why not? Let's do this. C minus P plus 2. So now I've got two components, two phases, plus 2. That's back to temperature and pressure. And I've actually already set temperature. Temperature's already set. And so pressure, if I do change the pressure, then I will control the composition. But if I don't change the pressure, I actually have T and P set, meaning I actually don't have any more degrees of freedom. So remember, this line, because this is at one temperature and this line's at one pressure, I've already taken my two variables and shut them down. If I've shut them down, I have no control. There's no degrees of freedom left. Those were the only two I had, and I decided to fix them. So, no, there is no more control, and this is exactly what this is showing you, that you don't control it anymore. Okay, now I'm going to do something a little differently. I'm going to start here, and I'm going to pour more A into the solution, so forget these for now, I poured more A into the solution. Instead of setting it up differently, I poured it in. And I'm over here. What in the hell? Now you tell me how to say again. Before I just poured different amounts to begin with. But now I've opened up the container, poured more A in, directly added stuff to it, and closed the box again. And of course, I still maintain the pressure by magic. I don't know how to do it. But I closed the box. Now, what happened to that A? Because it seems to have magically disappeared because the compositions are still the same. So where did that liquid that I poured in that came to equilibrium, what happened to it? Where do I account for its mass? There's more there. Why did the compositions not change when I physically added more after equilibrium was established? All right, so that's the answer. See, I'm closer to the vapor phase. And that means I have more vapor. Now, is the vapor more rich in A or B? Right, it's left of half, right? So, the system, to fight you, remember, this is like a Le Chatelier's deal. The system didn't like what you did. You perturbed the system. It fought back. It fought back, and also to maintain the fact that you don't control it, by making more vapor, which was rich in A. That's where your extra A went, to the vapor, which had more of it. It can't do the opposite. It can't go to liquid. Couldn't make more liquid. That would actually suck. That would actually release more A, not absorb it. So again, the Le Chatelier answer was to make more vapor, which was richer in A, and it made so much vapor that all that A you poured in, all of it was vapor phase, every bit of it. And that's how it relieves the stress. Now, of course, again, as I mentioned before, in terms of the Gibbs phase rule, if I do extreme things, like so much A, okay, yes, I can perturb all this if I push it hard enough. But again, when I want to talk about changes, I'm talking about differentials, so I'm talking about small changes, all right? So while in this example, I don't have control, yeah, if I push it hard enough, I really do, but then again, that's akin to cheating, so we won't take it that way. All right, so homeworks.